And so first of all, are there any questions on what we've been doing? Nope. OK. How was the tutorial yesterday? It's good. OK. So what I wanted to do today is get to the kind of the headline algorithm of quantum computing, which is Shor's algorithm. I probably won't have time to get all the way through it today, but we'll then finish it tomorrow. So Shor's algorithm is an algorithm for factoring large numbers. So what's factoring problem? I mean, you can probably guess. So, so given some number n, our goal is to find non-trivial p and q such that n is equal to p times q. And now normally what we're really interested in is finding the prime factors of n, and frequently this is done in the case where n is the product of two prime numbers. But that's not really essential. And of course, if you can solve this problem with p and q potentially composite, then you can kind of iterate and factor p and q as well until you get indeed to the prime factors. So one thing that's maybe worth pointing out, so this problem as phrased this way is not a decision problem, right? It's giving outputs that are numbers, not just bits. But it's easy to convert it into a decision problem if you choose to do so. There's not really much reason to do it, but just to understand the conceptual structure of these things, which is, so you can ask, here's the decision version. So given n and m, does n have a factor, let's say a non-trivial factor, less than m? OK? So clearly, if you can answer this question, you can answer this one, because you find out the prime factorization, and then you'll see if any of those prime numbers are less than m. On the other hand, it may be slightly less obvious, but it's still not difficult, given this decision version, to answer this question. So how would you do that?
Set m to the square root of n.
Set m equal to the square root of n. OK, so that will tell you whether it has a prime factor. I mean, there's not really any much point in going bigger than square root of m, because you can't have both of the factors bigger than square root of n. But just trying one value of m is not enough to tell you what the prime factors are.
Increase m into your
binary search.
Yeah, so you want to do a binary search. So you start out by saying, oh, let's let m be, I don't know, square root of n over 2. OK? And well, OK, let's start out with square root of m to answer the question of whether it's prime or not. If it's not prime, then we do square root of n over 2. And if it has no factors less than square root of n over 2, we know that the smallest prime factor is between square root of n over 2 and square root of n. And then we can try 3/4 of square root of n and say it does have a prime factor less than that. So then we kind of narrow down the window. We know there's a prime factor between square root of n over 2 and 3/4 square root of n over 2, and we narrow it down further and further and further. And we only have to do that about log n times. That's the important thing. And so this thing, assuming we have an algorithm to do this in polynomial time, polynomial in the size of the input, which is log n, then we'll get an algorithm that solves this thing in however long it takes this times log n, roughly. OK? So it's still going to be a polynomial time algorithm. So these two things are basically equivalent. So that gives you an idea of how these kind of function problems relate to decision problems in some cases. OK, so the other thing to notice about factoring is that it's kind of the inverse problem of multiplication. Multiplication, I give you two numbers, p and q, and I ask you what is the product, p times q. Okay. And of course, we know how to do that. You learn that in elementary school. And the time to do that is going to be some simple polynomial, like in the log of the numbers p and q that you're given. Well, you're supposed to learn it in elementary school. Maybe you forgot since then. But so the point is that factoring takes a time that's, say, log n squared. Sorry, multiplication takes time that's like log n squared. And you can do better than that using more clever algorithms. But factoring, people have worked on this quite hard and have yet to come up with a good classical algorithm to do that. So the best known classical algorithms, sorry, it's not the best known algorithms, the best known algorithms use a time that's kind of roughly e to the log n to the 1/3. Okay, so this is not quite exponential in log n, but it's certainly super polynomial. It's called sub-exponential time. And in fact, a lot of people have worked pretty hard on trying to find such an algorithm, because it turns out that if you can factor large numbers, you can break a widely used cryptographic system called RSA. So what is RSA? So RSA is an example of a public key crypto system. So let me first explain what a public key system is. Cryptography. I'm having trouble spelling today. Okay, so in a cryptographic system, we'll talk a little bit more about this next week in the context of quantum cryptography. But we have generally two people. Alice is trying to send a secret message to Bob. Okay, but somewhere along the way, there's Eve, who might be tapping into this communications line and reading the messages that are being sent from Alice to Bob. Okay, so Alice wants to encrypt her messages so that in such a way that Bob can decode them and understand what she's saying, but Eve cannot. Okay, and this is usually done using some sort of secret key that's not known to Eve. Now, in a public key crypto system, there's a public key. And the public key might be known to everyone. And in particular, it's known to Eve. And the public key is used to encrypt messages. In other words, you take a message that anyone can read and convert it into a secret message that not everyone can read. And then there's a private key, which is known only to Bob, in this case. And that's used to decrypt the messages. And one of the main properties of this public key cryptography is that it's an asymmetric protocol, that a different key is used to encrypt messages and to decrypt messages. So the way public key cryptography works is that Bob will generate a private key and a public key together, and then he'll publish the public key somewhere. Give it to Alice, post it on his webpage, whatever. So then when Alice wants to send a message to Bob, she'll use that public key to encrypt the message, send it over some open, non-secure communications line, like the internet. And even if Eve is listening in, she can get the ciphertext. But she also knows the public key, but she doesn't know the private key, because Bob has never made that available to anyone else. Okay? And so only Bob can decrypt the message. Okay? And classically, these public key crypto systems rely on a computational assumption, usually. I mean, there's other variants that rely on some other kind of assumption. The computational assumption is of the form some mathematical problem, some computational problem, is too hard for Eve to do. Okay? So there's a limit on Eve's computational power. Okay? So does this make sense? Okay, let me run through RSA so you'll see a concrete example. So how does RSA work? So RSA is named after its inventors, Rivest, Shamir, and Edelman. Although it turns out it was actually known to the British cryptographic agency, GCHQ, some years before it was discovered in the public domain. So RSA, like I said, it's based on the hardness of factoring. And in particular, what it works on is modular exponentiation. So, so for the key generation step, so this is before anything, any message is sent. So Bob picks two large primes. P and Q. And we'll let n equal P times Q. And so this is the kind of the basic mathematical core in that Bob, that n is going to become part of the public key, but only Bob knows the prime factors P and Q. Okay. But in fact, usually the private key and public key don't explicitly mention the prime factors. It's kind of there implicitly. So Bob is also going to choose, in a way I'll tell you in a little bit, some E, which is going to be less than n, and finds D such that x to the ed is equal to x mod n for all x. Okay? And again, I'll tell you in a little bit how to do this. So then the private key is D, and the public key is the pair n and e. Okay? And so encryption works by taking some message x, which I'm going to assume is some number that's less than n. And then we take that, we encrypt that into a ciphertext. This is the term for an encrypted message, which is x to the e mod n. So you see this is a calculation that's relatively straightforward to do given e and n, which are part of the public key. Right? Because, yeah, okay, so in a way I'll talk about later, raising x to the eth power, even though e is quite large, that's something that's easy to do, right? Because you can square repeatedly. And I'll give you more details about it later, because we need that as part of Shor's algorithm. And then taking the remainder modulo n, that's certainly easy, right? You just never have to keep track of anything bigger than n. So this is a procedure that Alice can do knowing the public key. And then the decryption, well, you might be able to guess from what I've said so far, but let me say it anyway. Is so given a ciphertext then Bob, since he has the private key, raises it to the power d. And so he gets a decoded message, which is y to the d mod n. Okay? And because of this property of E and D, we know that this thing x prime is equal to x to the e to the d mod n, which is x to the ed, which is equal to x mod n. So Bob gets back the original message x. Okay? On the other hand, if Eve gets a hold of the ciphertext, well, she doesn't know what d is. So she doesn't know what power to raise it to. Okay? Okay, so various things to say about this. So let's see. So first of all, I assume that this message x is less than n. Of course, it's possible that you have a much longer thing that you want to send. What you can do is you can break it up into chunks, right? And each chunk is going to be about log n in size, and so you can encrypt them separately. And actually, that's not really what you do. So really what you do is the x is actually going to be a random number. And you use that random number as the key for another symmetric crypto system. And the reason for that is that Alice, because the public key is public, Eve knows it as well. So Alice can encrypt messages, but actually Eve can encrypt messages as well. Eve is not, in this case, trying to fool Bob by sending fake messages. You can use a different protocol to take care of that. But the issue is that suppose Eve has narrowed the message down that Alice wants to send down into one of two possibilities. Right? She knows a lot about what Alice and Bob are doing already, but she just doesn't know whether Alice is going to say, let's meet at noon or let's meet at 6 p.m. And that's what she wants to figure out. So the thing is that if Alice were actually encrypting directly the actual message, then what Eve could do is she could just encrypt both of those two possible messages herself and compare with the ciphertext. Okay? But by sending a random number, that's no longer possible to do because there's a huge number of possible random numbers. Okay? So that's a kind of a technicality in how RSA is used. It doesn't really affect the mathematical structure here, but that's what you use when you're using RSA and the internet to send your credit card, for instance. That's what's going on.
Is there a standard for what kind of symmetric?
Yeah, I mean, so there have been a variety of standard things. I think the most commonly used standard nowadays is something called AES. And these symmetric crypto systems tend to be much less mathematically elegant. I mean, this is kind of using some basic number theory. I mean, I haven't really even shown you the basic number theory yet, but I will in a second. And symmetric ones are a little bit messier. And so on the other hand, they also tend to be more secure in the sense that, well, for instance, we know how to break this on a quantum computer. And there's a sub-exponential time for breaking it on a classical computer. But I don't think we know how to do either of those things with AES, for instance. Yeah?
So I'm not sure I understand what you mean when you say x is a random number. You mean she encrypts it before? She encrypts it twice?
No. Well, OK. So again, this is kind of a digression. But what happens is Alice generates a random number x and encrypts that using RSA. And then she also sends, she uses x as a key to this other crypto system, which gives, so if Alice and Bob had already shared x ahead of time as a private key, so they both have it, then there's this other crypto system, AES or something, that lets Alice encrypt the message, send it to Bob, and then Bob uses x to decrypt it as well. Okay, so Alice is going to send her actual message encrypted using that secret key x. But the problem is Bob needs to know what x is in order to decrypt it, and so she sends that using RSA. Okay, so the advantage, I guess I should say, of this public key crypto system is that Alice and Bob don't have to have this pre-shared private key. That the only thing that kind of needs to be distributed is this public key, and you don't need to worry too much about the security of that, because that even Eve can have that. Yeah.
So you're saying that doing this double layer thing, Eve would have to have already broken RSA, like in an honest sense, to get X in the first place, and then.
Right. I mean, well, so right. I mean, so Eve could break either of the crypto schemes used here, but since RSA is probably weaker, that's probably the easier one to go after.
Isn't like the way something like AES works? You can kind of, using this X as like a hash to encrypt your message, and depending on your hash, you can encrypt kind of any message to any random string of stuff. So without you really can't break.
No, I don't think that's true. AES is still computationally secure only. Now, there's something called the one-time pad that we'll talk about next week.
Right.
That really has this information theoretic security property.
Right. Okay.
And you could, in fact, use one-time pad with this. It's just kind of unwieldy and annoying.
Right.
OK. Yeah, I mean, I guess the other, we've talked so much about this, I might as well say this. So the other reason they do it this way is that AES is a lot faster than RSA, both to encrypt and decrypt. And so just having send one key that you can use kind of for the whole long message is much better than having to break up your message into small chunks and send each of them by RSA. So that's a kind of technical thing, which is a digression on the digression. OK, so but to get back to the main point, I wanted to show you a bit of number theory. And in particular, there's a step here that I kind of skipped or just said, which is how Bob chooses E and D. And that's really important because E and N are public knowledge. And I want to explain to you why Bob knows how to pick D, but Eve does not. OK, so oh, yeah.
Also, we need to choose P and Q before.
P and Q, yeah.
P and Q before.
That's right.
And is an RSA prior to like primality testing in polynomial time? So like how could?
Yeah. OK. So yeah. So historically, yeah. Actually, I guess I don't know the whole history. So before the deterministic primality testing algorithm, there was a randomized primality testing algorithm, which was, so this was something that we knew how to do in BPP, basically, but for a long time not in P. And actually, the randomized algorithm is more efficient, in fact, than the deterministic one. So still nobody uses the deterministic one. It's just kind of an interesting theoretical result. Now, at the time RSA was discovered, I think they probably didn't even have the randomized one. But the kind of the basic concept behind the randomized one will actually be easier to explain in a moment. But it uses Fermat's theorem, which has been known for a long time. Let me get back to that in a second. So, yeah, I mean, so the whole business of how do you find good primes, I mean, in fact, you have to be kind of careful. It's not just enough to pick just two random primes. There's a little bit of cryptographic art, I think, that goes into picking good primes. And what I'm going to tell you about how to find E and D, again, there's some cryptographic art that goes into picking good values of E and D so that you don't end up with an accidentally easy case.
Or if the NSA sends you the wrong values of E and D so that they can happen.
Well, that's right. And so there's some evidence that the NSA has kind of influenced the company RSA in kind of, I don't think, so I don't remember exactly what kind of cryptographic product, but this sort of thing can be a big deal in the cryptographic community, but it's really not the topic of this course. So before I spend all the time discussing that stuff, let me move on. So the basic mathematical result here is Euler's theorem, which, as you can tell by the invocation of Euler, dates back quite a ways. So what that says is that for all x less than n, x to the phi of n is equal to 1 mod n. OK, so what's phi of n? Phi of n is sometimes called the Euler-Totient function. And it's equal to the number of natural numbers less than n, which are relatively prime to n. Okay, and so there's a relatively simple formula for this in terms of the prime factorization of n, and in particular, if n is equal to p and q, in this case p and q are prime, so that's the case we're most interested in, then phi of n is equal to p minus 1 times q minus 1. Okay. So to getting back to how you pick primes, in the case where n actually is prime, then phi of n is just p minus 1. And so that's saying that x to the p is congruent to x mod n, or mod prime, which is known even further ago than Euler, is Fermat's theorem, Fermat's Little theorem. This is kind of gives you an idea of how you can pick primes. You pick some random value x, take it to the power p, and see if it's equal to x, mod p. And if it's not, then you know that p was not prime. If it is, well, you have some evidence that p is prime, and you keep doing this for a bunch of x's. But unfortunately, it turns out there's occasional very rare numbers which are not prime but still have this property, that x to the p is equal to x mod p. So the actual, the real rigorous randomized primality testing, you have to do some additional stuff beyond this. But most of the time, that will kind of get you the right answer. Anyway, so getting back to RSA, so using Euler's theorem, we can figure out. So Bob knows p and q. So in particular, he knows how to calculate phi of n. Okay, and so Bob is going to pick some random e, although as I said, it should actually not be totally random. There's some guidance for how to do it, but he'll pick some random e, which is relatively prime. To phi of n, okay, and then using Euclid's algorithm, which takes even longer, and which we did in the tutorial yesterday. So using Euclid's algorithm, he finds some d such that ED is congruent to 1 mod phi of n. Right? So this is just a rephrasing of that formula for Euclid's algorithm. Right? This is saying that E times D is equal to 1 plus something times phi of n. Right? And Euclid's algorithm finds you that constant here, but also finds you the D. Okay? And then once he has this D, well, then it has the desired property, right? Because x to the ED is going to be x to the 1 plus something c times phi of n, right? Which is, well, x to the phi of n is equal to 1, so this is just equal to x mod n, as desired. Okay? So, but the point is that to do this, you need to know what 5n is. And to know what 5n is, you should know what the prime factorization of n is. Okay? So that's why if Eve can factor n, she can run this whole process herself. And based on the public key, she can figure out the private key D. Now, it's believed, although not known for sure, that that works the other way also, that if Eve can break RSA by finding D, then she can also factor large numbers, or at least it's kind of similarly hard. But like I said, we don't know that for sure. OK. So other questions here on RSA?
So how do you get D? Like, how do you get D to begin with? Because you need them to be like, we need these to be quite large, right?
Yeah. But primes are not actually that rare.
Okay.
So the density of primes is like 1 over log n.
Yeah.
So even if you just pick random numbers, kind of within a reasonable amount of time, you'll find a prime.
Yeah, just go to the NSA website. They'll suggest some to you.
It's good putting off the list.
Yeah. So there's more.
3.
I think there's more clever things rather than just picking random numbers. Obviously, you shouldn't pick even numbers, you know. But basically, it's not that hard to find primes. Other questions?
And then using Fermat's level theorem is you can show something's prime.
Well, you have to use, like I said, you want to use one of these more sophisticated primality testing
Yeah,
algorithms.
right. But I mean, so yes, it's harder. It's explicitly harder to find the factors, to find 2 factors of a number that's not prime than it is to
That's right.
prove that it's
That's
prime.
right. That's right.
Okay.
Yeah. Other questions? OK. So now let's move a little bit closer to the quantum side, although I'm still going to stay classical for the moment. And in particular, what Shor's algorithm does is not directly factor numbers, but it solves another problem called period finding. So period finding, so we're given some function. And it's going to map the integers mod n to themselves. And let's see, do I want to? So this is going to be a periodic function with period r. And I'll assume that f doesn't repeat other than that. So we have f of x is equal to f of x plus r. And this is going to be mod n arithmetic. So n minus 1 plus r is r minus 1. But f of x is not equal to f of y unless y minus x, unless r divides y minus x. OK? And then the problem is find r. OK? That problem makes sense? I mean, any questions about the statement of period finding? OK. So let me tell you how period finding is related to factoring. So there's a couple of kind of mathematical details that I'm not going to go through. But basically, if you can period find, then you can factor. And in particular, we want to find the period of this function. f of a, which is x to the a mod n. Okay. And we're going to do this for multiple different x's. So it could be possible to do this kind of in general. So the basic idea is this. So our goal, well, OK. So here's where the period finding comes in. So what happened to the calc? There it goes. So what we're going to do is we're going to use period finding to find some x with even order. Okay, and then once we have an x with even order, we'll let y equal x to the r over 2, right? Because that's well defined when r is even. And that means that y squared is equal to 1 mod n, which in turn is equivalent to saying that y plus 1, y minus 1, so y squared minus 1, is equal to some multiple of n. Okay? So based on this, remember that n is equal to p times q. So there's kind of three possibilities here. So option 1 is that n actually divides y plus 1. Option 2 is that n divides y minus 1. And option 3 is that these factors p and q are split between these terms. So p then divides y plus 1, and q divides y minus 1. Or vice versa, but we can just switch which is p and which is q. OK, so let's consider these three possibilities. Well, so this one doesn't happen. So why not? Well, this is saying that y is congruent to 1 mod n, right? But y is x to the power r over 2. That would be saying that x to the r over 2 is equal to 1 mod n, which is saying that the period of this function is actually r over 2. But we know it's not. It's actually r. So that doesn't work. This one would be a problem. This is saying that x to the r over 2 is equal to minus 1 mod n. But it turns out that if you just pick random x's, well, sometimes the period won't be even. And when it is even, sometimes you'll have this happening. But there's some constant probability that as you pick x's, you'll eventually get something where the order is even. And I mean, for each time you try it, there's a constant probability that you get something where the order is even, and this is not true. OK? And so what we're going to do then is we're going to keep picking x's until we get these two things. OK? And so once we do, we know that we're in the third case. OK, so can I fit this on? Yeah, probably. OK. So we know that p divides y plus 1, q divides y minus 1. And y plus 1, we can easily calculate those. We don't even have to bother with this one. Let's just do this one. So we can calculate y plus 1. And then what we can do, since we know that p divides y plus 1, and it also divides n, we're going to let p be equal to the GCD of n and y plus 1. Okay? And again, this is something you can calculate using Euclid's algorithm. And once we have that, well, this is going to be, certainly it's a factor of n. And we know it's a non-trivial factor of n because that's the case we're in. Okay? So, so this gives us one factor. And of course, the other factor is q is equal to the GCD of n and y minus 1. Okay? Does that make sense? Yeah.
I failed to follow your arguments against case 1 and 2. If you
Right. So, okay. So case 2. Okay. So let me actually, there's something maybe I should have said it more explicitly. So this function is periodic, right? Because when we take x to the power r for some r, we'll eventually get 1 mod n. And then when we take it to the power r plus 1, we get x again. So which is the same as f of 1. So the period of this is the smallest value r, for which x to the r is congruent to 1 mod n. And y is x to the r over 2. So this one is saying that y is equal to 1 mod n, which would say that actually the period of x was r over 2, because x to the r over 2 would be 1 mod n. Okay, so we know that's not the case, because we actually found the period, which is the smallest value r. Okay, so that eliminates this one. This one, this can happen, but it's something that's easy to check. We calculate y, and we see that it happens to be minus 1 mod n. So what we're going to do is we're going to keep picking random x's and calculating the period until we get one that has even order, that has even period, but which doesn't have this happening. Okay, and then we move on to here. Yeah.
How do we know we can find quickly an axe that has even order and?
Right. So yeah. So there's some number theory that goes into that. I can't give you the argument. The point is that if you pick an x at random, there's a pretty good chance that it will have those properties. Kind of constant, independent of the size of n. So the odds are very good that if we pick a couple of them, that we'll find one. Yeah.
I'm not sure what you mean when you say that x has to have even order. I'm not really sure.
Yeah, I want to find an x that has even order. So that has this property that x to the r is 1 mod n, where r is even.
Okay. Thanks.
Right? That's the order of this function. Sorry, the period of this function. The order of x is if you look at kind of the multiplicative group generated by x. Multiplicative ring, anyway.
So period is a property of the function for all x, and we're looking.
No. So the period of this function f sub x.
Yeah. Okay.
So it's a period of specifically for a specific value of x.
But in general, it would be for all x of a function.
Well, I mean, so you know from Euler's theorem that the order of any element x, which is the period of this function f sub x, is going to divide phi of n, right? But it could be less than that, and there'll be a lot of numbers for which it is less than that. Other questions? Okay. So then, for the last little bit, let's move on to the actual quantum stuff. And give an overview of Shor's algorithm. Okay, So, so it's going to start. So there's going to be basically 2 registers. And each of them is going to have multiple qubits. And we'll start both of them in all zeros. And so this register here is going to have our value A at the start. And this one we're going to use to calculate x to the A, mod n. But that's just notation. At the moment, of course, I mean, that's just for intuition. At the moment, of course, they're still all zeros. And the first thing we do is Hadamard everywhere here. OK. And then we calculate, on these registers together, we calculate x to the A mod n. And then we can measure these things, although actually that's not really necessary. And then we do the Fourier transform here. And then we measure these qubits. And then there's some classical post-processing.
Wait, where are you substituting in x?
Sorry?
Where are you substituting the x to the mod n? Where does x come in?
Yeah, so x is something that's been classically. And then we run, so this is remember this is a period finding algorithm.
Right.
So what it's really doing is that this thing here, you're actually just computing that function f. Mm-hmm. OK, which in this case happens to be x to the A, because that's some, kind of the
Right.
main advertised use of Schur's algorithm.
Again, we have to have like n of those inputs on each of them, something like that.
Yeah, OK, so there's going to be each of these registers. There's going to be n qubits here. This one, I guess. So this could actually be bigger than n for reasons that I'll explain probably tomorrow. This one can be log n in size, because it's never going to be anything that's bigger than log n. But let's go through. So let's see. So the Fourier transform. Fourier transform is the discrete Fourier transform, mod n. Sorry, not mod n. This is n qubits, so it's mod 2 to the n. So in particular, it's this unitary. So applied to the basis state A, it gives us sum over b, omega to the AB b, where omega is 2 to the nth root of unity. Okay. And so let's go through, as we did for Deutsch's algorithm, and try to understand what's happening to the state at each of these steps. So let's see. So step 1, step 2, step 3, step 4, step 5. And I'm going to make a simplifying assumption, which is not actually the case, but it'll help us understand the intuition behind Schur's algorithm, which is let's assume that this period that we're trying to find divides 2 to the n. OK, so step 1, obviously we have the state 0, 0. And at step 2, what happens? Well, we've done the Hadamard on the first n qubits. So now they're in a superposition of all possible values. That's something you've seen before. So we have a sum over A of A tends to 0. Then at step 3, well, now we've done this modular exponentiation. So what we're doing is conditioned on this first register, we're computing x to the A mod n in the second register. So now we have this potentially entangled state, sum over A, x to the A mod n. Okay? So far, so good? So now let's look what happens when we measure this second register. So we'll get some particular value here. Let's call it y. And so y is going to be, for some particular value of a0, we can say that y is x to the a0 mod n. And so what we have left over for the rest of the state is sum over a such that, that x to the a is equal to y mod n of a, which the thing is that we know that a0 has this value, and the function is periodic. So that all the values of a that work here are a0, a0 plus r, a0 plus 2r, and so on. So really what we can do here is take the sum over multiples of r of a0 plus jr. Okay, so this is going to be, this is the leftover state on the first register. And so this is a state that looks kind of like this, with a distance r between these spikes. Okay? And so now we move on to step 5, where we've taken the Fourier transform. So what does the Fourier transform do to a periodic function? Well, it extracts the periods. And in particular, this is discrete Fourier transform. Let's calculate this out a bit more explicitly. So what do we have? We have the sum over j, and this basis state here goes to the sum over b of omega to the a times b. So what is a? A is a0 plus jr. And so this is, we can change the order of summation. So we have omega to the a0b, and then put the sum over j inside. Sum over j, omega to the jrb, and then b. Okay. Now let's look at this sum. Well, so if b happens, so this is so this is, remember, a 2 to the nth root of unity. So what we're taking here is the sum over e to the 2 pi I jrb over 2 to the n. Okay, and let me rewrite this a little bit as 2 to the n over r, which I'm going to call alpha for the moment. And so if b is a multiple of alpha, an integer multiple of alpha, then this thing here is an integer, and this is just 1, right? So if b is equal to c times alpha, then we're just adding 1, 1, 1, 1, 1, 1. And so it's just a question of how many terms we get here, which it turns out to be alpha. On the other hand, if b over alpha is not an integer, then we still have some root of unity, non-trivial root of unity. And as we add over j, we're taking different multiples of this root of unity, right? And they'll go around the unit circle. And roots of unity, when you add multiples of them, they're going to be evenly spaced around the unit circle. And so when you add them all up, you get 0. Okay, so by doing this sum, I mean, this is really just kind of the same thing that happens when you do a Fourier transform always, but worth making it explicit since you might not be as used to this discrete case. And so the upshot is that this sum here is only for the multiples of alpha. So this, we can take the sum over this multiple here. And we get omega to the a0, and then b has to be c times 2 to the n over r. And here we have c 2 to the n over r. Okay? And then at this last step, well, before the classical post-processing, let me go over here. So we measure, and get out some multiple. I mean, the phase here doesn't matter anymore. So what we're getting is this, c2 to the n over r. And remember, 2 to the n over r, we're assuming is an integer. So, so we're getting some multiple of that integer. And if we can figure out what that integer is, what alpha is here, then we can figure out what r is. So the classical post-processing is to do this a couple of times. Because we have some multiple of 2 to the n over r, not exactly 2 to the n over r. And now we have different multiples of 2 to the n over r. And so we have alpha 1 is equal to c1, 2 to the n over r. Alpha 2 is equal to c2, 2 to the n over r, and so on. And then we can take the GCD of these alphas, which, with high probability, because the C's are completely at random, with high probability, we'll eventually get the GCD has to be 2 to the n over r. Right? It'll always be some multiple of 2 to the n over r, but if you pick enough of these alphas with very high probability, it will be exactly 2 to the n over r. So we get 2 to the n over r, and that in turn tells us r. Okay, so that's kind of the overview of Shor's algorithm. I don't really have time to get into the details today, but we'll do that tomorrow. And I'll tell you how to do these various steps in more detail. Yeah?
I mean, if I was to find, if I was to find this, if I was to do this, and then I got the wrong, say I got 2 to the n over r times by some c.
Right.
If I was to invert that to find r, then I would find that, I want to say I'd find kind of a half period or something, right?
Yeah, potentially.
And so you could just, you could just go and check this and say, oh, this hasn't repeated by then.
Exactly. And even more deeply, if you're using this as part of a subroutine in a factoring algorithm,
yeah.
suppose you don't pick up that there's something wrong, and you go through all of this and you find things that you think are factors.
Yeah.
Well, what you can do is you can divide them into n and test that.
Yeah.
It's again something that's easy to do. So yes, that's right. So all of this is checkable, and in fact, you should check it because there's some randomized stuff going on. And as we'll see tomorrow, once we remove this assumption, there's even a little bit of extra randomness that's coming in, and so you won't even actually necessarily be getting a factor of r. So yes, that's important to do. And so I guess the other thing I want to say is that, I'm presenting Shor's algorithm for its application in factoring. But of course, period finding can be kind of an interesting problem in its own right. It actually turns out that there's a number of different public key crypto systems that can be broken by Shor's algorithm. Not every public key crypto system that people have ever come up with, but certainly the ones in common use. And people have come up with all sorts of variants of Shor's algorithm that solve other problems, not necessarily very practically interesting problems, but it's a kind of a broader technique. And actually, later this week, probably on Friday, I'll show you another application of Shor's algorithm. OK, other questions? Yeah.
So, because you're saying that like we don't know whether quantum computation can efficiently model all of P, total of NP rather, this means that you can't use Shor's algorithm to break K-sets, right?
That's correct. That's correct.
People are always worried about if we make a quantum computer that's going to break RSA. You could replace that by some kind of similar version based on K-set.
Well, easier said than done. Nobody's managed to come up with a public key crypto system whose security is based on an NP-complete function. So one issue, so people have come up with ones that are kind of based on breaking something that looks a little bit like an NP-complete problem. But the problem is that for these cryptographic applications, you really need a problem that's not just hard in the worst case, but hard on average.
Right.
Right? Because, along the way, we had to say, oh, let's generate a private key, public key pair. Okay? And generally, we're going to do that by picking it at random, because if there's a deterministic way of doing it, then everybody will know what it is, and it doesn't help. And so you need, it doesn't really need to be all the possible values are hard values. But there need to be a lot of hard ones. And you need to be able to efficiently generate a random hard instance. Okay? And for a lot of NP-complete problems, that's challenging to do. There certainly are NP-complete problems where kind of most instances are easy, but then there's a few instances that are hard. And it can be, there's no necessarily straightforward way of telling whether it's an easy instance or hard instance. And besides all of that, you need enough mathematical structure. It's not just, you can't just automatically say, oh, here's a problem, let's make a public key crypto system out of that. Public key, you need kind of extra properties, something called a trapdoor function, basically, so that you can decode.
Yeah, right. So if we didn't have Euler's theorem, you wouldn't be able to.
That's right. So that's an important part in this case.
Right.
So the upshot is that people have made crypto systems based on other problems. There's a class of crypto systems that we don't know how to break with quantum computers. So that possibility does exist. But it's definitely not something that's, unlikely to be something that's NP-complete.
Right.
Okay? So so there is another solution that quantum offers, which is going to quantum cryptography. And I'll tell you about that next week. And it doesn't do exactly the same thing as public key, but it solves a similar problem. OK, other questions? OK, then tomorrow we will go into the guts of Shor's algorithm. You'll see how the modular exponentiation and the Fourier transform work, and what happens when R is not dividing 2 to the n.